So depending on which height point you choose, we named it differently. There's no word regular here. It's left Riemann sum, right Riemann sum, midpoint Riemann sum, general Riemann sum, right? And we choose xk star bit midpoint, left endpoint of the interval, right endpoint of the interval, anything different. So I'm showing you today lots of different irregular partitions. The very first one, this one's not really irregular, right? This is a regular one, right? This is a partition method. Do you recognize the first one? K times b minus a divided by n. That's a regular partition. The second one, if you throw in a positive number alpha there, that doesn't matter as integer or not, this is going to be increasing. You can see when k equals 0, you start from a. When k reaches n, this becomes 1. So a plus b minus a, you arrive at the end point of the interval b. So I'm choosing this part different. All are increasing function starting from 0 and ending at 1. All these values in here, as k varies, starts from 0 and ends at 1. So all this x1 through xn is distributed over that interval, but not necessarily regular fashion, according to this function. And you can see as we vary, there are infinitely many more different partition methods, right? So regular partition method, and there are infinitely many more irregular partition method. So there are methods there. So here's a general description. xk, you started from a, and you go all the way up to b minus a. So whatever you throw in front of the b minus a, it has to be an increasing function. You start with a 0 and ending at 1, then it'll satisfy this partition method. So there are infinitely many different ways of doing the partition method. And here's a choosing height points. Let's get here, that's the partition points. These are the, so what is the good name of the first xk star? Midpoint, thank you. That's the midpoint. What about the second one right here? What is a good name for that? There's 0 multiplied to xk minus 1, right? So this 0 disappears and only survives with xk, which is right endpoint. So this would be the right endpoint. This is the choice we use for right Riemann sum, right? Right Riemann sum. How about here? Third one? Let me explain that point. So what kind of point is this talking about? Here is xk minus 1. That's left endpoint of the interval, right? This is right endpoint of the interval. And this point is in between these two endpoints. And what kind of point is it going to be? Is this 3 suggesting you're going to divide this into 3 pieces? Whether it's going to be the first piece or second piece, the answer is actually the second one in here. So it's a 2 to the 1 is cross-multiplied like that, and you get that point. So I remember that formula. So this point will be 2/3 to the way to the right. So overall, we're choosing this point if you throw in this formula. You can distribute like this coefficient 1/3 and here's a 2/3. These are the coefficient if you distribute it. The rule is that if you actually have any coefficient like this, such that a over a plus b, b over a plus c, if you add them together, it becomes 1. Any positive number in front of it, if they add up to 1, then it's going to define some sort of midpoint in there. So it's going to be consistent, but even you can change this one. Sine squared and cosine squared. As soon as you see sine squared and cosine squared, what comes to your mind? Add them together equal 1, right? So these are the nice parameterization of a two positive number added to the 1. So if you throw in these numbers, for the first interval I use certain ratio, second interval I use a slightly different ratio, third interval I use a slightly different ratio. These are consistent throughout all the intervals. Now you can even change that. So these are all different choices of height points, right? So let me show you the next slide. So the idea is this: you can throw in any increasing function, any coefficient, even varies with k, such that they add up to 1, and they all contribute to very different methods of partition and different ways of choosing height points. So let me introduce this notation. Pn denote a partition method, some formula that has n and k in it. So if I vary n, you know how to further divide it, right? If you have a computer or a patient, if I give you n equals 500, you can use that one of the partition method formula, keep plugging in to get this 500 points in between 1 and 3, for example. So you have that mechanism ready. So you also choose the Pn star. It is the our choice of height points. Suppose you have a formula that I described there, so you know how to choose these points in between each of the interval, no matter what n I give you. So you have these two formulas. So those are called one partition method, and this is called choice of height points. Once you have this thing, then we can define what is called Riemann sum correctly. But when you say the partition method and choice of height points, we assume that these intervals keep getting refined. We don't want to leave one big chunk in the size of like this. It never decreases. So we have to look at all the interval length of each of the partition into n subintervals. We have to assume that all of them as together is refined into going to 0. The maximum value of the length of this interval eventually must be small and small. So these are the notation. This is of summation, Pn and Pn star. Finally, I'm trying to define the meaning of this symbol, which was just introduced as a signed area using the picture and our intuition. Nobody questioned the meaning of the area, but they wanted to define carefully in mathematics. It still takes time. It's not the immediate definition here. Given a partition method, you have a formula for xk equals log 1 plus n divided by, you have a formula given, and you also have a formula for height points. So whenever whatever n I give you, you know how to compute those. If, sometimes it doesn't happen, if the following limit exists, we're going to denote that by L subscript, depending on this partition method and depending on the choice of height points. What is that limit? Is the sum here as n approaches infinity. So what is this Riemann sum, right? What kind of Riemann sum is it? Is it left Riemann sum or right Riemann sum? Or is it a midpoint Riemann sum? None of those three, right? This is just general Riemann sum, right? Not necessarily our point is midpoint. It was just general formula we're throwing in there. Given any partition, any choice of height points, we consider this one. All you have to change is the n value, right? What's going to happen to this limit? If that exists, that limit value is going to be denoted like this: L subscript P, P star. So if I give you a different partition and different choice of height points, this might go to different value, right? So you have to use LQ and Q star if it is different partition. So this thing, the setup makes sense? Next one is a true definition of that integral, definite integral. If there is a number L such that over all different partition method I showed you, and infinitely many more, and they're all different choice of height points, and there are infinitely many more there, this limit value for each of the method, LP and P star, right? Each of the partition method and choice of height points, there's this value. They're all equal to each other. If that amazing thing happens, then we call that L to be the signed area of the region. If there's one partition, this group calculated, this limit was 5, and this group computed with a different partition method, Q and Q star, they got 6, then we say the area is not well defined. But if it happens all the time, then we say it's defined. Of course, there are infinite many ways. There's no way to check one by one. We have to mathematically argue that actually happens. All right, that's my version 1. Nobody likes this one version. It's too many quantifiers and complicated. So this is my second version, and people like it better. So this one represents, as a notation, the assigned area, and it is defined to be the limit of this Riemann sum, and this limit has weird symbols down there. It's not n approaching infinity, right? Partition method is varying, your choice of height points is varying, and n is going infinity for given two choices. So I want you to remember the definition of definite integral in this fashion. I think is easier, right? Okay? And I'm going to call that one wordy definition. And this one is the concise definition of definite integral. Fair enough? All right. Now you know what the mathematical definition of assigned area is. That's that. And here's the theorem. We just said that you can't deal with all the partition. There are infinitely many more. So what I'm going to do, there is a theorem. It's called Theorem of Integrability of Continuous Functions. If a function is continuous on the interval a to b, that thing I was talking about, this involves consideration of all possible partition methods and choice of high points. Doesn't matter. They all go to the same value as long as the function is continuous. Even if there's nowhere differential, crazy fractal shape function, they still go all the same value. So I'm going to call it TICF, Theorem of Integrability of Continuous Function. To understand mathematics logically, this becomes an important foundation. On top of it, we can do more calculation in there. It only says about the existence of that L, right? It is not telling you how to compute that L. It's just existence of L. All right? So you have that understanding, definition versus this theorem. What we actually do once you understand the content of the theorem is the following. If it goes to the same value, no matter what, why don't we choose the simplest partition and simplest choice of high points, right? They all go to the same value anyway, right? So what is the simplest one? Regular right Riemann sum. You don't have to choose a midpoint. Simplest one is formula-wise the simplest. Regular, choose right endpoint. Everything is simple. Then that regular right Riemann sum will approach whatever that L value was asserted to exist by the theorem of integrability of continuous functions. So we're going to focus on regular right Riemann sum, right? Okay. So here's a complete formula of the regular right Riemann sum. So I want you to figure out where that b minus a divided by n come from. Where did that come from? What is b minus a over n in terms of partition notation? Size of the partition, that interval length right there, right? Delta x, they're all same. It doesn't vary with k. So we can set outside linearity of this sigma notation. How about inside in here? F of is supposed to be xk star, right? This is supposed to be xk star, but we choose right Riemann sum, so this is just right endpoint, xk. And this is the formula of xk for regular partition. All right? So I want you to go ahead and have a, chance to write this one completely down. You're going to just use all the time, not, for this class and the next class, to compute this definite integral. This is your exercise number 1. Everybody gets full 2 points. Just write this one down. If possible, do not look at it and try to write it down on your own in terms of A and B and K in a very, very explicit form. All right, how was it? Was it all right? This is delta x, f of xk star again. That's right endpoint of each interval. Any question about this formula? So whenever you're asked to compute the regular right Riemann sum, you write this one down as exactly like this verbatim and identify what your b and a and n is, and you're going to calculate the sum. All right? And what does this arrow mean? As n approaches infinity, right? Now once you have this formula ready, simplified, and send n to infinity, what's going to happen if that's 5 and that's your answer, definite integral being 5. All right? Any question? Let's look at this caution. It said this is not the definition. The definition of this definite integral has 2 things: wordy definition and precise definition. Under the limit, there's a p, partition varies, height of choice of high point, p star varies, and it goes to infinity. That's the definition, and this is a theorem that you can calculate that through this regular right Riemann sum. Right? I asked you to learn about this summation notation, and before I go into the summation notation, this is a picture of Riemann, student of Gauss, and who thought out this and decided to do it a little bit more carefully, and it's named after him is Riemann sum. How about this notation?